stronger the intermolecular force, the higher the melting point or boiling point. So it's going to require more energy to break those individual molecules away from each other. Okay? So as we talked about with 4, 3, and 2, in 4 we have an ionic bond which generates an ionic force. With 4A we have hydrogen bonding, a polar covalent bond which generates hydrogen bonding force. Ionic forces are stronger than hydrogen bonding. The ionic force wins out. That's going to have the higher melting point or boiling point. We move up to 3. What forces are we comparing?
Polar bond versus a hydrogen bond.
Okay. So we don't want to mix our metaphors here, so let's kind of fix that. So a polar bond versus, what would the other one be? So if we're saying 3A is a polar bond, what should we be looking at in 3B? The bond. What is the bond in 3B that I'm looking at to compare to 3A? Okay. Hydrogen bonding is not a bond, so that doesn't count. Dipole-dipole is a force, also not a bond, doesn't count. If we're going to reference 3A as polar bond, we had better make sure we're looking at the same reference when we move to 3B. What are we looking at? It is a polar bond. Okay. So what I heard shouted out for explanations was someone was telling me 3A is a polar bond and then 3B is hydrogen bonding. Okay. Those are two entirely different systems. Saying an apple weighs more than a cucumber. That's a fruit and a vegetable. It's not a fair comparison. We can't make that comparison. You have to make sure you're looking at the same comparison. So if we're going to look at 3A as a polar bond, what part of 3A is the polar bond? The oxygen bound to the carbon. That is now our polar bond. So when we move to 3B, we have to look for our bond. And what's the bond that we're going to find in 3B? Okay. I hear OH as our primary one. That's going to be the most important one to be looking at. And that bond is? The not hydrogen is a good way to answer that. It is not the hydrogen bond. Remember, I'm asking for the bond. It is a polar bond. It is the polar covalent bond. Okay, the reason I'm addressing this, are they different?
Different bonds, but they're the same.
They're the same type of bond, which means we cannot use that as our comparison for which has the higher or lower of anything, because it's the exact same thing. Okay? Okay. Take it a step further. Melting point and boiling point, as Johnny suggested at the beginning, are based off of the force. What we've just identified is the bond. You're not answering the question that you need to answer. The bond is helpful because we can use that information to then classify the type of force that comes from it. And a polar bond will generate which type of force?
Carbon.
Carbon is an atom, not a force.
No force.
Will be a dipole-dipole force. Okay? So it's a dipole-dipole force in both cases, which then means they're again the same. That kind of sucks. We can't tell a difference. Except the instant you see a dipole-dipole force, you should be thinking in the back of your head, is there a stronger dipole-dipole force? Yeah, what is that stronger dipole-dipole force? Hydrogen bonding. To have a hydrogen bond, I must have a dipole-dipole force. Hey, I looked at that. Okay, what else do I need to have a hydrogen bond? Hydrogen. Bonded to fluorine, oxygen, or nitrogen. So I go back to my structures and say, in my dipole-dipole force generated from that polar covalent bond, I have an O bonded to a C. Is either of those hydrogen? No. So do I get hydrogen bonding coming out of 3A? No. In 3B, we decided to look at the OH bond. Is one of those a hydrogen? Yes. Is that hydrogen bonded to oxygen, nitrogen, or fluorine? Yes. Which means? Instead of looking at dipole-dipole, I should be looking at hydrogen bonding. Which is the stronger force, hydrogen bonding or dipole-dipole? Hydrogen bonding. The stronger force means the higher melting point, and our answer becomes 3B.
So is it still a polar bond, or were you just messing?
It is still a polar bond. So, and I'm not messing with you, okay? When you say, I want to compare which is the better fruit, and I'm going to compare broccoli to apples. Broccoli's not a fruit. You can't make that comparison. Okay? So when you're answering a question, you better make sure you're answering the question and not making up nonsense explanations. Yes, they're relevant terms, but that doesn't mean that gets to the root of what you're comparing. Okay? And this is something that is common, is you think you have an answer and you'll dictate it out and you'll come up with that explanation, and the words are associated in the correct thing, but entirely wrong context. Right? So when we're looking for melting points and boiling points, what that is asking for is the strength of the intermolecular force. How do we determine the intermolecular force? We have to identify the bond that is present. Once we have the bonds that are present, we can then backtrack to the forces. Once we have the forces, we can then say which is the stronger force. Once we know the stronger force, we can then say we have the higher melting point and boiling point. But at no point do we make the comparison polar bond to hydrogen bonding. One is a bond, one is a force. Those are entirely separate categories. Does that make sense?
One tutoring center told me they were in the same categories.
They're wrong.
Okay.
I can go back and yell at them. They're wrong. Okay. So one of the things that tends to come up is an over-interpretation, and that's why we're trying to very clearly delineate these things as separate categories. Okay? Bonds and forces. Okay? And it's made more confusing because hydrogen bonding sounds like a bond. It's not a bond. Not a bond. Okay? So let's move to 2. Are we good to move to 2?
Yeah.
So should we try this as just a bulk shout out again? See where we go?
Sure.
Okay, what's the answer to 2?
B.
B. Okay, and of course the follow-up question will be, why? So we've got an easy answer on the why. And these... What determines our melting points and boiling points? Forces. So if we're saying 2B is the answer, what's our why? 2B has a stronger force.
Oh.
Why does it have a stronger force? What is the force in 2B? Okay. So let's do a review here. Forces on the right, bonds on the left. Okay. Forces require multiple molecules. This question is asking you to apply out to multiple molecules and think about how they would interact with other molecules. Okay. So when we go through and look at these, we have to kind of process through that. 2B, we're saying it has the stronger force. What is that force? Okay. Theoretically, you got there by doing all of this work, but maybe we don't know that force. Okay, maybe you didn't get the answer right. Okay, so we have to backtrack. Well, to get the force, what do we need to know? What kind of bond? So we need to look at 2B and say, what are the bonds that are present? Okay. This could go all the way back to my favorite, which typically tends to be most general chemists' least favorite, Lewis structure. Because when we look at those formulas, what we're expecting you to actually have done is recognize that this is your structure. So that when you look at that formula, you say, oh, that's the structure. The bonds that I have would be carbon to hydrogen. carbon to oxygen. Oh crap, that's it. Sorry, I thought there was another one. Right. If those are the two bonds, what types of bonds are those? What is a carbon to hydrogen bond? A nonpolar covalent bond. Nonpolar C, because I'm out of space. What is a carbon-oxygen bond? A polar covalent, or a polar C. A polar C generates which force? A dipole-dipole. A nonpolar covalent bond generates London dispersion. Which is the stronger force? Dipole-dipole. Okay? So I know the strongest force in 2B is dipole-dipole. And in that sequencing, I didn't even ask about 2A. Do we have to know what's going on in 2A to answer the question? Yeah, because what's the question? Which one has higher? It's a comparative question. You have to know what's going on in the other one. So if we go through and look at the other one, again, boiling all the way back down, you're expected to know, is it really hot in here?
Yes.
Yeah, I'm kind of dying. You're expected to know that that is your structure. What types of bonds are there? Or sorry, what bonds are present? Carbon to carbon, carbon to hydrogen. What is a carbon to carbon bond? Nonpolar covalent. Carbon to hydrogen. Also nonpolar covalent. A nonpolar covalent bond generates what force? What is the strongest force coming out of that compound? London dispersion. What's the only one, so we don't have to worry about it. Now that we have the strongest force in each compound, now we can make the comparison. We're not saying it's a nonpolar covalent bond being compared to a hydrogen bonding force or a dipole-dipole force. Okay, we have to compare the same class. You good? So the answer was 2B. Okay. And the moment we've all been waiting for. What's the answer?
B.
Sorry, I had to do that. Everybody had a minor heart attack. It is 1B. Why is 1B the answer?
Size matters.
Right. If we go through our arguments that we've been making, we have to go back, evaluate the strength of the force. We identify the force by looking at the bonds, comparing the bonds, and working our way all the way back up. Right? And if we do that argument, what are we going to discover? That they are both London dispersion forces. Right? Well, then how would we decide which one has the higher melting point or boiling point? Interestingly enough, no one said that they're both the same on the quiz, which is interesting. Oh, you did? Oh, cool. I didn't read that carefully enough.
Wait, did you want us to tell you why?
No, I didn't.
Okay.
It was A, B, or same would have been an option.
All right.
Right? How do we determine the difference? Well, what keeps these two pieces of paper together?
A connection.
The connection between them, right? It's the surface of that paper touching the surface of the other paper. Right? So there's an attractive force there. Right? What happens if I then take those same two pieces of paper and wad them up into little balls and now look at the force attracting between them? Why is it less? It's the same paper.
Less surface area.
It comes down to the surface area. So it's the same strength of force, but I have less opportunity to make that force. Which then means I get a weaker attraction between them. So you would have a lower melting point. So when we go back and look at these two compounds, what is the only difference?
The amount of bonds.
The amount of carbons in each of those structures, the amount of atoms. Right? One has a slightly larger structure, which then means it has more opportunity to make those weak London dispersion force attractions, which then means a higher melting point and boiling point. So when we're looking at our melting points and boiling points, the first approximation needs to be the strength of the force. Okay? But then we need to factor in other things, because there are situations where the strength of the force is the same. We also have to look at the amounts. Does that make sense? And don't worry, those weren't your quizzes. That was the other class. And it actually was the other class. I'm hoping I don't forget. Okay? Makes sense. Nice touch on the same though. So, phase transitions. What happens if we look at our heat being supplied to our sample and the temperature? So let's say take a block of ice. And actually, we're going to step back from our block of ice here in a second. And ice is blue, right? So let's make it blue. Whenever we've got a graph, and this is something that you need to be able to pick up, is interpreting different graphs. And this is something that typically does not get discussed or taught. You're just kind of expected to learn it. Okay? So let's look at our graph and try and come up with some interpretations. Okay? So some things that we might want to do, what are the axes? Okay? So one is labeled cleanly heat, and the other one's labeled T. What was T? Okay. That was our temperature. Okay. Might be nice to know what they're being measured by. So what unit might we expect for temperature? Kelvin's not a bad one. Okay. How many of you know the melting point and boiling point for ice or water in Kelvin? Too long? How many of you know it in a different unit? Degrees Celsius. Does anybody know it in Fahrenheit? That I find so mind-bogglingly weird, right? We live in the U.S. where what temperature unit do we use? Fahrenheit. And yet nobody knows the melting point and boiling point for water. The time it took you to come up with 32 and 212 versus 0 and 100 was pretty shockingly different to me. Whatever. Yeah. So, heat. What is our unit for heat? We did briefly talk about it. You may or may not remember. It's okay. Joules, typically what we're looking at for our heat. Okay? It's our unit for energy. We're putting energy into our system. Okay? So we've got some units. We've got some labels on it. The other part we want to do is make sure we have a concept of what different points on our graph mean. So I'm going to pick a point, and you need to tell me what you know about that point. That little black dot, lower left hand. What can you tell me about that point? It has no temperature. That's an interesting observation. Okay? I'm not saying 0 temperature. I'm saying no temperature. It's not even on the temperature axis. Okay? So it's a useful statement to make, but we should get a little bit more information about what we do know something about. We know it's on the heat axis. What do we know about that point? Say that again.
Low energy.
It is low energy. So, well, that's kind of obvious, Mike. I didn't need to say that. Except if you don't make that obvious statement, you misinterpret the graph. Okay? So how can we make sure that you make that obvious statement without shouting out the answer in the middle of an exam? It is low heat. Doesn't have to be hard. And then conversely, of course, what do we have at that other black point? That is high heat. Okay. Any guesses where I'm going to go next?
Middle heat.
Temperature. Purple point. High temp.
Wait, no.
We already have low and high. What are you referencing?
The temperature, so it's coldest at the top.
Okay, so there's an interesting point. Going with a term that represents temperature. Okay, it's cold or hot. If we're at the top, we're at a very high temperature value. So pick a high temperature value. 105. Is that hot or cold? That is hot. Okay? So the simple act of processing through some of these terms can help us nail down what we're looking at. So at the top, we're now hot. And at the bottom, we would be cold. Okay? Simple labels. So now let's go through and deal with our little block of ice. I'm going to say the ice starts at what temperature? Let's pick a temperature. Everybody likes to pick 0 because what happens at 0? We make ice, right? Okay. And potentially easy. I'm going to argue that that's not the best temperature to start at. I'm going to pick North Dakota, middle of winter, minus 40 degrees Celsius. Can ice be that cold? Yeah. Okay. It just happens we're not at a temperature or a phase transition. It can be that cold. Okay. What happens as North Dakota starts to warm up? How is it warming up? We're adding heat. So we're starting on our curve, our temperature, at which part? Cold or hot? Minus 40. Cold. Okay, so we can add a little bit more information here. We're actually at minus 40 degrees Celsius. Okay. As we add heat to the ice, what happens? So we're going to start to move this direction. The temperature increases. Okay, so the temperature goes up. Okay? So the temperature is increasing as I add heat. Okay? Then something magical happens. At what point? Zero degrees Celsius. What is at 0 degrees Celsius? Changes phase. It moves to a liquid. So I'm adding this heat, and I've now achieved my 0 degrees Celsius. What happens as I continue to add heat? This was a solid. Begins to melt, so it starts to become a liquid. Okay? But there's still ice present, which means what's the temperature? Still cold, yes, we can quantify it. It's still the freezing point, which means our temperature is 0 degrees Celsius. As I continue to add heat, what happens to that solid ice? It continues to melt. There's still ice present. So what happens to the temperature? Still 0. So an interesting feature is happening here. I'm adding heat, and what happened to the temperature? Stayed the same. Until what happens?
The center of the ice cube is melted.
There's now no more solid ice. Now I have liquid water. What happens as I continue to add heat? Now the temperature starts to increase. So I heard a suggestion for it starting to boil. What temperature am I at? 0 degrees Celsius. So am I going to boil? No. All I'm going to do is take that 0 degree ice water and turn it into not ice water, to maybe some drinking water, okay? Then to maybe bath water, and then maybe into hot tub water, and then to maybe I'm now cooking my lobster water. And at that point, what happens? I've now reached 100 degrees Celsius, as it feels like this room is becoming. And what happens again? The temperature is going to flatline yet again, because I have to add heat. I'm still adding heat to that pot of water. Once water gets up to boiling, it doesn't all of a sudden instantly move into a gas. It sits there until eventually it becomes a gas. Okay? And it's still moving. Where's it getting that energy to move? From the heat you're still constantly adding into it. So your temperature will stagnate at each of those phase boundaries until eventually what's happened? It's now, I don't accept all gone. Can't destroy matter. It's all turned into a gas. And now what happens? Now the temperature can increase again. So if you've heard kind of stories, oh, somebody got burned by steam. Oh, come on, it's steam. It's 100 degrees Celsius. Okay, yeah, that would hurt. You might say, well, it can't be that bad. But the issue with steam is that's gaseous phase. What is the upper limit on gas? There is none. So I can have gaseous water at thousands of degrees Celsius. That's kind of dangerous. Okay? So when we're looking at hot gases, they aren't just 100 degrees Celsius. Our gases can be several hundreds of degrees Celsius, if not thousands. Okay? There is no upper limit on that. Sort of.
So temperature is supposed to measure the kinetic energy of the molecules moving around. So when you say it flatlines there, are the molecules not moving around faster until the phase change happens?
Until our phase change has officially changed, our kinetic energy doesn't change. Okay? So we've got a couple kind of observations that can come out of this. We can look at the energy it takes to heat a sample up without a phase change. In that process, what happens to our temperature? Our temperature changes, right? So we'd be looking at, say, I don't know, the measure of energy we put in like joules, per like the mass of the sample, and say the temperature change. Those units look somewhat familiar. Those look kind of like the units for specific heat. Okay. But what happens when I move to a phase transition? Am I still adding heat? Yeah. I still have to get that phase to fully transition. So I'm still adding energy. But if I looked at my specific heat, what's happening to my change in temperature? It's not changing. So if the change in temperature is 0, I'd be having an energy term divided by 0. And if we punch that into the calculator, it usually freaks out and says error. Okay? That's because mathematically we can't interpret that correctly. So we have to account for that energy term some other way. That energy term is known as the energy required for that phase change. So if I'm looking at, say, the heat to transition between the ice, I shouldn't say ice, let's say solid. That's what I'm looking at. Like all my stuff has disappeared. So, yeah, what is right? The solid. Hopefully this is working. This is our liquid, and this is our gas. I have no idea what it's doing with the recording. Hopefully that works. Okay. If I'm looking at the transition between the solid and the liquid, that's going to be the heat necessary to do what? The heat necessary to melt it. Okay. What if I look at the next plateau? That would be the heat to do what?
Boil.
We could do the heat to boil. There's actually a fancier term for melt, but I don't think anybody's going to know that one. But you might know the one up here. Heat to go from liquid to a gas. The heat of vaporization. Okay. That would be going from the liquid to the gas. What happens if we went from the gas to the liquid? That's our heat of condensation, right? Because we're now going the opposite direction, so we can't call it the heat of vaporization. What would the magnitude of that number be? Let's say the heat of vaporization is 10. What is the heat of condensation? Same number, but opposite. Opposite in magnitude. And it becomes a minus 10. Because we're either adding energy in or taking energy out. If we go down to the solid and liquid, this is the one I always get confused. It's the heat of fusion or the heat of, I don't even remember. But you will typically use that if you have to move into, say, 151. You get lots of heat applications, and you're looking at this curve and trying to quantify each of those energy transitions. Okay? What's going to determine how much energy you have to put in there? What's going to determine how much energy we have to put in to, say, cause a species to melt? The intermolecular forces that we just talked about. Okay? So, next one. Vapor pressure. We talked about vapor pressure before. What was vapor pressure? Don't all shout it out at once.
The pressure of
Vapor, yes.
evaporating.
It is the vapor, so it's the gas state, that's the pressure, but it's that vapor coming from a liquid. So if we have a liquid phase, how much of it is naturally already moving to the gas phase? Okay, so we have evaporation processes and we have boiling processes. Boiling is the full-on phase transition. Okay? Vapor pressure or evaporation is just saying it's naturally doing it kind of on its own. So if we look at intermolecular forces, how could we apply it to this? So based only on intermolecular attraction, predict the following liquids has the highest vapor pressure. Okay, so I removed the answer choices because we want some context on this first. Okay. What does a high vapor pressure mean? We said vapor pressure was the amount of gas. There's a lot of gas. So if I look at an individual liquid, okay, I have a lot of gas. Okay. Why is it a gas and not a liquid? Said the other way, why would I have just a liquid and not the gas? What's preventing it from becoming a gas? We could say atmospheric pressure, but all of our compounds are going to have atmospheric pressure. That's not a bad idea. And I'm hearing something about temperature come in. What are you referencing with temperature, actually? Thinking about the specific heat, kind of, yeah? We're looking at the tendency for a liquid to move into the gas phase. Liquid moving into a gas phase. That would be the, I don't know, the boiling point? Yeah, right? Liquid to gas, that's the boiling point. And what controls the boiling point? Temperature, sure, but if I'm given a list of structures, they're all going to be at the same temperature, so that's not going to work. The intermolecular forces. Oh, I wonder why that picture was right next to it. Okay. We're being asked for the largest amount of gas. Okay. Which means our substance is dying to make it into the gas phase. Which means what about its boiling point? I should have a very low boiling point. Okay. We're going to add another little term here. Has anybody seen these little 3 dots? Okay. Pretty sure that at least how I learned it was therefore. Okay. So highest amount of gas. Therefore, lowest boiling point. Lowest boiling point doesn't say intermolecular force, so that doesn't help. So therefore, how do I get a low boiling point? I have a weak force. Based off just the question asked, based only on the intermolecular attraction, which of the following liquids has the highest vapor pressure? So we're going to see a list of liquids. Are a list of liquids the same thing as a force? No. So, therefore, not necessarily weak liquids. How do we determine our forces? From the bonds. And we'd be looking at the That's where we got to be careful. A weak bond is an ionic bond which generates the strongest force. So what we're looking for here is actually the strongest bond. What is our strongest bond? It is our nonpolar covalent bond. The ionic bond, which is what people again tend to associate, but associate incorrectly with strength, is because you think of an ionic compound as a solid. That's not its bond, that's its force. You generate the strongest force in an ionic compound because it has the weakest bond. Okay? So if we're looking for our strongest bond, we need to find a compound that has nonpolar covalent bonds all the way through it. Okay? So what we would go back and do, now that we've done all of that legwork and written it all down, and I'm going to regret that. Oh, maybe I won't regret it. Let's see. We would then go back and look at our answers and see if we can find one that has just nonpolar covalent bonds. What do we see in A? We see OH, which is polar covalent. I don't care what kind of force comes out of it because I'm looking for a nonpolar covalent bond structure only. OH doesn't match that. How about B? Every bond in B is a nonpolar covalent bond. Cool. B seems to work. Let's make sure we aren't getting tricked and there's another correct answer. C. We have that OC, which is polar covalent. That doesn't fit the pattern we just went through and looked at. D. We have our polar covalent with that chlorine bound to, and this is the tricky one, bound to the carbon back from it. And the last one, polar covalent because we have that sulfur bound to our carbon. Only one answer was only nonpolar covalent. The answer is B. We're done. This is a tricky question because it requires you to do all of those tiers, which is a ways back, but I can tap back hopefully to it. There it is. We can tap all the way back to all of that processing. You have to process through each and every single one of those things to get at what you're actually being asked. Which of those compounds has only nonpolar covalent bonds? That's really the question being asked. Okay? You have to know all of the chemistry content behind it. Okay? And believe it or not, you do. Questions on that?
So the strongest bond is the weakest force.
The strongest bond generates the weakest force. Okay? So this gets a little bit weird. I need to fix my kind of curls on this. Okay? What we're looking at is officially a full spectrum of colors all the way out, nice straight line. Halfway in between, we have a delineation between forces and bonds as a spectrum along the bottom. Okay? And what's happening is we increase the strength of the attraction to the left. The furthest to the left we are, the strongest attractive force we have between those atoms. The furthest to the right, the weakest. Okay? So we could show this as just a straight line graph. But the issue with the straight line graph is that doesn't show us the relationship between a nonpolar covalent bond matching the weakest force. Does that make sense? I chose to organize it in the ring instead of the straight line to accent that matching across of our bonds and forces. Okay? So our strongest bond is our nonpolar covalent. Our weakest bond is ionic. Why is ionic such a strong force? Well, it's a weak bond. It's such a weak bond that it becomes force. Where is it on our force list?
Low side.
On our force list?
That looks like the low side to me.
Okay? That says weak.
Oh,
That would be low.
you were standing there.
Our ionic bond becomes such a weak bond that it's actually a force. And it becomes the strongest possible force. It's such a strong force that it eventually becomes a bond, depending on where you draw that line. Yes?
You said the strongest bond is between one molecule, right? Like table salt. There's a bond.
Yes.
Okay. Then the opposite was between intra.
Yeah. So our forces are between molecules. And this is where ionic compounds have weird gray area. What's the molecule in table salt?
Okay.
Well, there's the repeating unit, but there isn't a full molecule. When we look at our covalent compounds, we have distinct molecules. When we look at benzene, we can't say CH, we have to say C6H6, which we talked about when we looked at our empirical versus molecular formulas. So ionic compounds fall in this weird kind of gray area category. They aren't really fully bonds because they aren't sharing electrons. They aren't really fully just forces because the strength of attraction between those atoms is so insanely strong that it starts to equate to them sharing electrons. Okay? We did that. Solubility. Okay? We've looked at some solubilities before. Right? You saw those. If I looked at the solubility, lower left hand, that's right hand, that's my right hand corner. If I asked you about the solubility for your ionic compounds. Sodium chloride and water. Would I expect those two to mix? Okay, yes? Why? Sodium is a group 1 metal. All ionic compounds with group 1 metals are soluble in water. That comes all the way back to our double replacement rules for predicting solubility. Right? Why do we need separate rules for our ionic compounds? Because the ionic compounds, depending on the salts generated, do some weird, goofy stuff. Right? The ionic compounds, remember, fall in that weird category between bonds and forces, and it becomes difficult to align and predict those. Right? So when we're comparing things that are equally polar, like water, we can start to make approximations a little bit better than we could with, say, the other compounds. So our ionic category is a whole separate system. So when we're asking about solubility now, what we're mixing are like bonded structures. So we're looking at covalent compounds with other covalent compounds. Okay? So you may have heard a common rule of thumb that like dissolves like, which I personally hate. I just keep saying that word. I don't hate things. I don't like the way it's used. Okay? It's not clear enough. When we're saying like dissolves like, we're saying like forces dissolve like forces. Which means when I look at a compound, what do I need to do? Determine the forces. Once I know the forces for compound A and the forces for compound B, I say, are those terms the same? What if they're the same? Then they mix. We're not comparing anything here. We're just saying, are they similar? We're not saying which one's higher or lower. It's just, are they similar? So if we take a look at water and ethanol, theoretically, everybody, well, most people know that one already. Are water and ethanol soluble? Yes. Okay. Which you should know probably from spring break and potentially a couple hours after the exam. I won't elaborate. How do we predict this? What are the forces in water? We have an OH bond, which is a polar covalent bond, which generates dipole-dipole forces. We can then add hydrogen bonding because we have a hydrogen bonded to oxygen, nitrogen, or fluorine. So the strongest force in water is hydrogen bonding. We go through and we look at ethanol. Well, we have carbon to hydrogen. We have carbon to carbon. We have carbon to oxygen, and we have oxygen to hydrogen. How do we know which one we should be looking at? It's really going to come down to practice. You've done enough practice that you're aware of which one you should be skipping to. If you haven't done that practice, guess which one you should look at? All of them. Good answer, whoever said all. Okay? You should look at each of those bonds and say, what type of bond are they? What type of force does it generate? Okay? Which we've done already. And in that process, what you should find is the one that generates the strongest bond is the one that is OH. Or sorry, the weakest bond, which is a polar covalent bond, which gets us which force? Dipole-dipole. Because we have a dipole-dipole, we can look for hydrogen bonding. Do we have a hydrogen bonded to oxygen in OH? Yes. We have hydrogen bonding. Which gets to the next question. Is hydrogen bonding like hydrogen bonding? That should be a quick question. Yes, yes, hydrogen bonding is like hydrogen bonding. Because they are similar, guess what happens? They mix. That's it. Ta-da! Hands-free. Next one. Should make you guys do it? Turn it into another quiz. No? Okay, so work it out. Prove to me you're working it out. H2O and propane. Do they dissolve? No. Why not? Not the same forces. The force for H2O is hydrogen bonding. The force for propane, London dispersion. Okay? Everybody getting this?
Yeah.
Shall I move on?
I had a question.
Yeah, go ahead.
I didn't figure, I just stopped once I found the hydrogen bonding. Is that a valid way to figure it out? Because there's no, you can just look, there's no hydrogen forces. Because there's no, because it's not going to equal.
So,
Like,
I think I know where you're going with that, but let's push what you stated and see if what you stated fully makes sense. Are those soluble? Water and what? So what you stated was I just found hydrogen bonding and then said they're not soluble. What's the issue? Found hydrogen bonding and what's the and? Saw that the other one did not have hydrogen bonding. Does that make sense?
That's what, yeah. Because they're not going to be equal, they're not going to be.
Yes.
Okay, that's what I'm.
There are levels to this because we can absolutely make it a lot more difficult, which I'm pretty sure you don't want me to do. Should we look at example or just let it go? I heard one say do it one. Just one. Just one. Just one. I promise. Just one. Which is more soluble in water? Propane, A, or propyl chloride, B? Wow, that was awfully fast. Okay. Do we have hydrogen bonding in either? No. So your example of just saying, well, it didn't have hydrogen bonding, so they're not going to mix, doesn't always work because I can change the question to be which one is more soluble. It could be crappy solubility, but it's still more. Does that make sense? Yeah. So why is B more soluble than A? B has the carbon to chlorine bond, which is a polar covalent bond. The polar covalent bond generates a dipole-dipole force. So what I'm comparing in A is London dispersion forces to hydrogen bonding versus dipole-dipole forces to hydrogen bonding. Which is the most similar? Dipole-dipole. Okay? So I might still say B's not going to dissolve in water, but it's going to dissolve better than the other one will. Okay? So we can do those kind of bulk comparisons with the forces. It's not just a blanket, oh, it doesn't or it does. Okay? We can do some kind of variation in between. thank you for letting me kind of veer a little bit. Okay. If we look back at water and solubility, where a lot of this is coming from, which we've already addressed, is looking at the structure of our compounds and the charges, the partial charges that come out of this. When we look at a bond in water between our oxygen and our hydrogen, I almost pulled out the white pen, that was going to be kind of dumb. Oxygen being more electronegative than the hydrogen takes most of the electrons from that bond. By accepting those electrons, it becomes partially negative. The hydrogen lost those electrons, so it becomes partially positive. The instant we generate these partial charges, they are trying to neutralize. So they will move into systems that neutralize those charges as best as possible. Okay? And in solubility, it becomes a little bit trickier because we aren't looking at just water on its own or just the other compound on its own. We're looking at those compounds individually on their own and then saying what happens if we mix them. Is that mixed situation stabilizing the charges as equally as well as the individual situations? So we've got lots of little interconnecting pieces moving between it. And it can make it a little bit more challenging to develop if we don't think about it on this kind of atomic level and evaluating the partial charge differentials. Okay? That's why that partial charge notation becomes important. That's why electronegativity becomes important. That's why structure becomes important. Because all of those things that we're using to predict how these things interact with each other comes back to applying those pieces and seeing how do they fit in a range. Okay? And that is what makes chemistry fun and entertaining and a good thing to study. All the math and quantification behind all of those observations can become tedious. Some people really enjoy them, some people don't. Okay? So, another question. Apply the like dissolves like rule to predict which of the following liquids is miscible with water. Do we need to do this?
Yes.
Yes. Talking about. The whole point is looking at differences in charges, electronegativities, and structure. Okay, so we have to have some concept of structure. So they gave us a bunch of names of compounds, which how many of you know what any of those names mean if we ignored those formulas for a second? Okay. Some people know, some people don't. You're not expected to know the names. Why are they listing the names? Kind of just for fun. They're sort of making it real. How many people have at least heard of some of those names? That's the context. That's why the name is being provided. It's a potentially misguided attempt to make chemistry seem more real. There are better ways to do that, but that's what they're trying to do. Okay? So if we just gave you the name, though, you wouldn't be able to figure it out, because to figure it out, what do we need? The formula, our structures. We need to be able to interpret that. So they did give us all those structures. And as someone pointed out, well, then they're trying to figure out what do those structures mean. Well, it starts off with like dissolves like. Like what? Forces. To determine the forces, we need the structures. The structures of how many compounds? 2. Like forces dissolve like forces. Presumably on a different compound, because we wouldn't be asking the question if it was the same compound, because then, of course, they would mix. Okay? So what we're trying to do is compare two structures. So if we look, we got the question, and then we have a list of structures. What's the immediate issue going to be? That's only one structure. What are you comparing to? Water. They gave you the name of water because they're assuming you know the formula. Okay? They could even potentially give you the formula, but it's probably a good idea to write it down. Remember when we talked about the formula for water? We could write it as H2O. And I said, generally, I like to write it as something else because it helps me see the individual pieces. What was that something else? HOH. Like forces dissolve like forces. What's the only thing like or thing that we can see within HOH? See H and we see OH. Are there H's in these? Yes. So that wasn't very helpful. But OH, A, no. B, no. C, no. D. Oh yeah, there's a lot of them. E. What's the answer? D. Okay. So the process that we've been going through, I've been showing you where these things are coming from. Some of you care about where they come from, some of you don't. What's the quick shortcut? Do you see the same piece in your answer as in the question? That's it. Okay? There are ways to hide that using different compounds. The practice exam has a few of them like that. In fact, these multiple choice came off the practice exam. Okay? So go through, look at those, think about them, and process them. Which gets us into our almost last exciting unit, looking at acids and bases. If we go through and name these compounds, what's the first one? Really? Everybody's giving me different names. Oh, but we don't need to know nomenclature for the cumulative exam. Oh, maybe we should go back and review that. That might be a good idea. We got time a little bit next week. We can go back and do that. We've got hydrogen. And we have sulfur. Hydrogen and sulfur are both nonmetals, so the type of bond we have is covalent or a molecular nomenclature system, which then means this becomes dihydrogen sulfide. What's the next one? Dihydrogen, I've got sulfur again, but I've got that oxygen. This is a complex ion known as sulfate. The T is a tip-off that you're looking at a complex ion. If you see the D in your name, it's a binary compound. Right? It's just the element by itself. Last one. Sulfuric acid. So all of these are very, very similar to each other, and yet, if I listed those names off at the beginning of the semester and said, which of those are you most concerned about, which one are you going to complain about?
The one that looks like
Sulfuric acid. Why would you complain about that one first? Because acid shows up in the name, and everybody freaks out the instant we say acid. Okay? So when we think about why this unit is important, this unit is so old that the term acids is tied back into our primitive brain as being something dangerous that we have to watch out for. That's because acids tend to be more reactive. That's why we have a special nomenclature system for them, to help warn people of what's going on. So what makes an acid? If we look at those three names, and in fact we could even compare the middle one, because the middle one's the most similar. What do all three of those, and why is only the last one called acid? We need the AQ, but I could take sodium chloride and dissolve that in water. If I took sodium chloride and dissolved it in water, it would be NaCl dissolved in water, AQ. So sodium chloride is an acid? No. What else do I need? Hydrogen. Right? So what if I take, let's ignore solubility for a second, methane, CH4, and I dissolve that in water. Does it have hydrogen? Does it have the AQ? Is that an acid? No. Why not? So the backwards analysis for this class is that acids yes, they're defined as hydrogen, a species having hydrogen and the AQ, but that hydrogen, to be considered as an acid, needs to be in front of the compound. Why does it need to be in front of the compound? When we think about acids, what is the reactive part of the acid? Okay. Comes out that it's the hydrogen. Okay? And so sulfuric acid got the different name because people went through and made observations on certain substances and noticed these general characteristics. Okay? And yes, you might be like, sour tasting? You mean somebody tasted these things to figure out what they were? Yes. It was a valid scientific method. Okay? And we used that. Okay? So sour tasting and sticky feeling. Okay? Or bitter tasting and a slippery feeling. We noticed that there were certain classes that had these characteristics. Right? And those ended up getting labeled according to our acids and bases. It turns out that acids are sour tasting and sticky feeling. Right? Bases are bitter tasting and slippery feeling. Anybody, we're probably all old enough now that no one actually had this happen. You swore when you were a little kid and your parents shoved a bar of soap in your mouth?
Oh, yes.
Yeah, how did that soap taste?
Delicious.
Okay. Typically tastes bitter. And soap, if we rub soap on our hand, is slippery. Guess what soap is? It's a base. Okay? So we were able to come up with these kind of comparisons, and these relationships are what we use to define the acids and bases. We then also found that when we mixed an acid with a base, it released lots of heat. That's because acid-base reactions are exothermic. They release heat, okay, because they're forming a more stable compound in water typically. Okay? So now that we've expanded our knowledge beyond sticking foreign objects in our mouths and seeing if it hurts, we need to come up with other ways to interpret our scientific data. And that's where we run into chemical formulas and looking at those formulas to come up with interpretations. Right? So we know we have an acid because we have the hydrogen in front, and we typically see the AQ afterwards. Do we need the AQ afterwards? For nomenclature in 130, yes, we do. Is it necessary for it to become an acid? No. Okay. Why do we need the AQ? Well, what did AQ mean? Aqueous. It meant dissolved in water. Why are we concerned about it being dissolved in water? Think back to all the reactions that you did in the lab. What was your solvent? Water. Okay. If you really liked someone or really hated someone, you can do the same thing, but in kind of different contexts. You could exchange saliva. One way where it was a nice process, the other way where you were launching it at them. Okay. What is in that saliva? Water. What is now pouring out of me copiously because of the heat? Water. Water is everywhere. It makes up, what is it, 70% of the earth, 80% of the earth? Our solvent for almost all systems happens to be water. So when we're going through a nomenclature system, we're trying to train you at the simplest level on what you're going to be exposed to. Well, what solvent are you more than likely going to be exposed to? Water. Which means we want you to be aware of the hazards of putting those chemicals into a water environment. So that when I take H2S and I add that to a water, what have I made? An acid. Right? Because I have that hydrogen in front and I've now added it to water, it's now AQ, so it's an acid. And I now know I have to watch out for that species. Okay? So at its simplest level, we're trying to give you some kind of those basics to it. But it's not the be-all, end-all. When we go through and look at bases, we have to say what's happening. So we're looking at our chemical reactions, saying what happens to each of those structures, how do they change? So when I look at that HC2H3O2, and I go across and look at the products, which of those products reminds me most of that compound? Which product? The very end. Why are you saying that very end? That's pretty close. Most of the atoms in that very end structure match with the start. Okay? What changed to that structure? So beginning to end, what changed? It lost a hydrogen and gained a sodium. Do I care about the sodium? Why not? It kind of goes full circle, actually. What was special about sodium? Generated always soluble compounds. It doesn't interact very well. I don't really care about sodium because it doesn't interact with things. Guess what hydrogen does? It interacts with things. Right? So hydrogen has a potential to be hazardous. So what happens in this reaction is really that compound in red lost a hydrogen. Right? So I will now label acids as species that get rid of hydrogens in the course of our reaction. Cool. I now have a definition for acids. What did it get rid of that hydrogen to? Something had to pick that up. Well, that's the NaOH. And if we look at the NaOH, the thing that looks most like it is the H2O. And what's the difference between those? It gains that hydrogen instead of the sodium. Right? So at a first blush, I can go through and say, well, the sodium, the first one had a hydrogen to get rid of, so I'm going to call that an acid. The next one had OH, so I'm going to call that a base. Does it have to be just OH? No, it could really be anything that could accept that hydrogen, which means my definition sucks. And yet, that's the first definition we work with when we look at acids and bases, which I'm not sure is the next slide. Oh, I was right, it is. Okay. Our acids, as our first definition comes down to Arrhenius, said when I add an acid to water, hydrogen ion appears. Ta-da, hydrogen ion. Okay. With bases, when I add the substance or the base substance that I think is a base to water, the hydroxide ion concentration goes up. Why look at the hydrogen ion and the hydroxide ion? That is what we'll end with and pick up with on Thursday. And it's also relevant to most of the discussion we had today.
Can I say the